Well, hello and welcome back to Engineering 201 Electrical Fundamentals. And as I'd mentioned last time, I wanted to finish up with our last lecture of an example, obviously a 6-step problem. And not that we necessarily need to do more 6-step problems, but I think this problem is going to be a good problem to finish up the term with, to give us some review going back and looking at 6-step, not only a 6-step, but also in terms of circuit analysis and coming up with voltages and currents and things like that. I don't know that this one will make us do any big long mesh analysis or node analysis, but if you've been struggling with why do I get a negative voltage when you get a positive voltage or vice versa, this one has a lot of those little tricks in it, so that'll give you some practice with that. So let's go ahead and begin. We recognize, as I said, this is a 6-step problem, has constant sources, a 12-volt source, a 4-volt source, and then this dependent source. So we note right off, no shortcut in this thing. And it has only one energy storage element. So we can solve it with our 6-step routine. And since we're looking for the voltage over there, I could say that V0 of t is going to be equal to K1 plus K2e to the minus t over the time constant. So all of our work then is going to be devoted to coming up with K1, K2, and that time constant. And like I said, no shortcut. So when we get to step number 5. Well, with that, let me go ahead and start to build this scorecard here, like we've done so many times in the past, so we can keep track of these things. We'll have several pages going before we're done with this thing and make sure that we don't get lost and lose information along the way. So we'll say that it's, the inductor is 2 Henry. And we can get started with this thing. We'll come back to this page, so I'll just set it aside. Well, step number, this was, of course, step number 1, right? So we then have step number 2. Is to assume that the circuit has been that way for a very long time. So this switch is open, so I just took this branch out, so we don't necessarily have to worry about that. The switch is not closed. If you want to think about this, this is time is equal to 0 minus before time equals 0. We have yet to close that switch. So I took the switch out, and remember that the inductor is going to look like a short since it's set this way for quite a while, and our task is to come up with a current through that. So I've labeled this current I sub L for the current through the inductor, and my task is to come up with that. So I could do a quick mesh or loop around here. If I start at this point, I have a gain of 12, so I could say that 12 is equal to, and then I've got 2 and 4, which is 6 times this I1, and then so I've gone up through here around there. That 6 is from 2 plus 4, and then as I come down through that, that's also a drop, so I'll put that on this side of the equation. I will say that that's positive 2IA. Now I can note here that this I1 going like this is actually just opposite IA. So note that I1 is equal to minus IA, and when I do make that substitution, I then have 12 is equal to 6I1 minus 2I1. Substituting that in, I get minus 2I1. So I have then what, 4I1 is equal to 12, so I1 turns out to be equal to 3 amps. And we can then say, therefore, that IA is equal to minus 3 amps. And the reason that I need that is because I can start to get this voltage. The voltage across here, which is just 2IA, is going to be the same as the voltage across here, right? And if I get the voltage across here, I can get that current. So let's do that. I can say that this voltage, V, right here, why don't I just call that V? I'll use an uppercase. Might be better to use lowercase, but I'll use an uppercase. The voltage V is equal to 2 times IA, which would give me 2 times a minus 3, which is equal to minus 6 volts, right? Okay, and now I having this voltage here, I really have that voltage there, don't I? That's V also. So I could say that IL at t equals 0 or 0 minus is going to be equal to, well, we know V is equal to IR, right? I is equal to V over R. So I'm going to take the voltage minus 6 divided by the resistance, that's 4. Okay, and I have to be very careful of this now, because the voltage like this, Ohm's law said that we would be finding the current opposite the voltage potential. This would be positive and negative according to this V, and my current would be going like that, but I'm taking the current going up, aren't I? So I would need a negative there because of how the current is opposite. The current needs to be opposite the potential. That is, this voltage potential here, positive and negative, the current needs to be going opposite that. So that comes from the direction of the current. So those negative signs cancel out, and I end up with positive 3/2 of an amp. Okay, 3/2 of an amp. Well, that's probably worth noting. So I sub L at t equals 0 minus, not 0 minus 1, is equal to, what do we have, 3/2 of an amp. Okay, so then going forward, I can take that into step number 3. Now, step number 3, all of a sudden t is equal to 0. I've moved the switch to its new position. I've closed the switch. I've thrown the switch. In this case, it's closing it. So, and then what we do, once we move the switch to its new position, I put this current source in. And remember that I found this I sub L going this way to the left. So I need to put that, I need to observe that direction when I put that source in there. So now I get down to business. I can finally start looking for this, the unknown, this voltage across this 4 ohm resistor when t is equal to 0. So a good way to tackle that would actually be fairly easy, wouldn't it? I mean, someone just told us the current here is what, 3/2 of an amp? So I could say then that V naught at t equals 0, or you could say 0 plus if you wanted to, 0 plus is going to be equal to, well, V is equal to IR, isn't it? So I've got the current 3/2, and then I have 4 ohms, and this is negative again because if I've got the voltage going this direction, Ohm's law said the current would have to go this way, wouldn't it? I mean, when we introduced Ohm's law at the beginning of the term, kind of, it's a good problem to finish up with. We go full circle on this. We were told that a current like this, I, is going to induce a voltage that is positive and negative there with some resistance. Well, what do I have here? I've got the current going this way. So I have this negative sign because of the direction of the current. Again, the direction of I, the current. Okay, so with this, I come up with an answer here that this is equal to, let's see, 6 minus 6. Minus 6 volts. Okay, so let me go back and put that in our scorecard. V naught at t equals 0 plus is equal to minus 6 volts. Minus 6 volts. So then we're ready to move on to step number 4. Step number 4, remember we just sit and let this thing, let some time go by. Let it go to steady state. So step number 4, where t is equal to infinity. So this thing becomes a short circuit. The switch is still closed. The switch will always be closed from here on out. And now I'm looking for this. I'm looking for this voltage V0 at t equals infinity. And how can I get that? Let's see. I could throw a current in here. What could I label? I guess I could label that minus IA. Could not? IA is going that way, so I could just say minus IA. So if I were to start at this point, I would have a drop of 4, because I'm going from there and moving around here, a drop of 4. And I don't have to worry about the current in here because I have a source, so I flat know the voltage there. It's not like I have a resistor in there. Then as I go through this one, I've got another drop. So I have positive 4 times, what's the current? Minus IA. So kind of an odd way of doing that, but I think you're up to it at this point in the term. And then we get down here, we turn and go down here, and we're going to go from positive to negative. So again, it's a drop. One thing to be careful of is this, it looks like this polarity here is a little bit different than we're normally used to looking at, so that's something to keep in mind as we go through that. But here we're going from positive to negative, so that's a drop, so I'll say it's positive 2IA. Gets me back down here to my starting point, so I can say this is equal to 0. Kirchhoff says that's equal to 0. So I have 4 minus 4IA plus 2IA gives me minus 2IA is equal to 0, or 4 is equal to 2IA. So in that case, IA is equal to 2 amps. Well, what good is that? Well, that tells us what the voltage across here is. I know that the voltage across here, the voltage across there is going to be equal to 2IA. Which happens to also be this voltage there. So I can say, therefore, that V0 at t equals infinity is going to be equal to 2 times IA. Right there, 2IA. So when I do that, I have 2 times 2, which gives me 4 volts. Okay, so I've got that. Let me go put that in the scorecard. So V0 at t equals infinity is equal to 4 volts. So I got 4 volts, step number 4. Then moving on, step number 5. Step number 5, and remember, no shortcut. No shortcut. It's not as simple as shorting things and opening things and looking back into those terminals. If we didn't have this thing, we'd be able to do that. Okay, but we have this dependent source, so we've got to work our way through this. We've got to go the long way and come up with our open circuit voltage, which I'll just assume my open circuit voltage like this. So why don't I say that that's V open circuit. And you might say, well, how do you know to take the open circuit voltage that way? It doesn't really matter, because as long as once I've committed to V open circuit, as long as I take the short circuit current the other way, I'm good. So had I taken the open circuit voltage the other way, I would have needed to reverse the direction of my short circuit current, and I'll show you that when we get to the short circuit current. So with that, let's see if we can do that. I think, again, I'm going to put a current in here. I'm going to say that this current going around here is minus IA. That seemed to work well for us before. So I can work my way through that. Let's see. I'm again going to have starting right there, a drop of 4. And then another drop of 4 times minus IA. Just again going around here. And now I have a drop, so positive 2IA is equal to 0. Kirchhoff says that's equal to 0. So again, I've got 4 minus 2IA, so is equal to 2IA on the other side. So IA is equal to 2 amps. Okay. Now, if this is open, the current through here, this current is going to be equal to 0. Okay, I is equal to 0 with open circuit, right? When that's open, that current is equal to 0. So V open circuit would really be the same as the voltage across here, wouldn't it? Which I could say that V open circuit then is equal to, what's the voltage from here to here? That would just be the opposite of this, minus 2 times IA. Minus 2 times IA. So you got to recognize that. And like I said, I mean, yeah, we got a mesh equation here. We've done a lot tougher meshes than that. But I think the really good thing about this problem is it's forcing us to recognize that V open circuit, what it is, that we have this negative sign here. So I'd carefully go through this problem. And again, I would encourage you to start from scratch and see if you can do it on your own. Well, we've agreed, hopefully, that V open circuit is equal to minus 2IA, so I can come up with a minus 2 times IA, which is 2. So I got V open circuit is equal to minus 4 volts. Okay, minus 4 volts. Well, now I've committed, and it looks like I've probably done it the wrong way since I got a negative sign, but that's okay. I'm going to put my short circuit current in here. So I'll put this current in here, and I say that's I short circuit. So if I'm committing to the voltage going from here to there, the current will have to be directing the opposite direction of that. Okay. So, and the other thing for us to get a positive resistance is we're going to expect, and we'd better get, the short circuit being a negative number. Well, let's see if we can go through that then. Well, with this problem, so this was all to find what? V open circuit. So if I look for finding I short circuit, what are we going to come up with? Well, we could go around here, and that would be exactly the same thing. Again, that would be 4 plus 4 times minus IA plus 2IA is equal to 0. Sometimes you get the same equation. Sometimes things will change. This shorting it out did not change this equation. Had there been a resistor right here, that would have changed that equation a lot. But there wasn't, so the equation isn't changed. So I can say that IA is equal to, same thing we got here, 2 amps, right? Okay. So if I want to try and find this current that's going this way, I'd better again find this voltage here, right? Why don't I call that V, so I can call that something. So what's V going to be equal to? Well, V is going to be equal to minus 2IA, isn't it? 2IA is negative positive. I'm going from here to there, so I'm going from negative to positive down there. So the voltage would have to be opposite that. So I can say that I have minus 2 times 2, which is minus 4. Nothing has changed so far. Remember, that was the same as V open circuit. But now that I've got this voltage here, the voltage is now going this way, so I can look at the current going this way. Okay, I'm going to cross this out then. So I'm not talking about, let's short it out now. So this is V, isn't it? So I can find this current, which is the same as I short circuit. So I short circuit is equal to this voltage V that we found divided by 4 ohms, which is equal to minus 4. That's 4 volts. Divided by 4 ohms, which gives me minus 1 amp. Okay, so then we can put this together, and we can say then that R Thevenin is equal to V open circuit divided by I short circuit, which is minus 4 divided by a minus 1, which gives me a positive. The negatives cancel. I get a positive 4 ohms. And I can breathe a sigh of relief. If this one is negative, I knew that this one had to be negative. I mean, at this point, when you saw that negative, you probably, we were happy about that, hopefully. Well, what do we do with R Thevenin? I mean, we could put this down here. R Thevenin is equal to 4 ohms. But more importantly than that, we're using that to get our time constant, aren't we? So the time constant is going to be equal to the inductance divided by R Thevenin. So I go back to my scorecard. What was my inductance? 2 henries. Make sure you use your base units. If it's a millihenry, go back and use henries. Use base units. So I'll have 2 henries divided by R Thevenin, which is 4 ohms, which gives me what? 1/2 of a second. Okay, 1/2 of a second. So let me put my time constant in my score sheet here. So time constant is equal to 1/2 of a second. Okay. So, like I said, this problem, we didn't have any really big, ugly mesh or node equations. We had lots of little things where it was easy to get mixed up. Make sure you know where that negative sign comes from. Make sure you know where this negative sign comes from as you go back and try this problem on your own. Well, let's finish this thing up then. So I've got I go back to my scorecard here. Got my scorecard filled out. And I should be ready to put this thing together. We said the solution was going to look like this. So we can use this information here and say then that K1 is equal to, what's that going to be? K1 is equal to the value at infinity. And then K2 is equal to, this is the one at infinity. And then K2 is equal to what you had at 0 minus what you had at infinity. What do we have at 0? Minus 6 minus 4. Excuse me, what? Minus 10. So K2 is equal to minus 10. So these are just little helps here. That was from our 6-step methodology. And so we can start to put this together that V naught T is equal to K2, which is, no, I'm sorry, K1, 4 plus K2, so minus 10, e to the minus t divided by the time constant, which is going to be a half. Okay, that's volts. I guess we could tidy this up. Our final answer is equal to 4 minus 10 e to the minus, let's see, half in the denominator, so 2 in the numerator, 2t. So 4 minus 10 e to the minus 2t volts. And that would be our final answer there. Let me double check that with my notes. Yes, I think we're good there. So, like I said before we started this problem, it's a good problem for review. It didn't come up have any huge node or mesh analysis. You've had some homework problems that are a lot more difficult in that regard than this, but it did really, I think, challenge a lot of people, or hopefully challenge a lot of people, hopefully set them on the right track and answer some questions about why you get a negative current versus a positive current, or a negative voltage versus a positive voltage. So I would encourage you again to go back and look at this thing, to take this thing and to start out with the original problem, to cover that all up, and see if you can tackle this on your own. That would be a great way to start your review for the final. Well, speaking of the final, we've got to the end of this class. So that's our last slide, page number 7. We've got to the end. Hopefully this has provided an adequate and good foundation for electrical study, for the electricals and mechanicals that go on. We'll spend a lot of time really backing up and doing much of what we've done already this term, but with complex numbers and AC analysis. So that should actually be a lot of fun. Like I mentioned, I think in the last video, if you don't have a calculator that can tackle complex numbers, you may want to think about that over the break. And if you do, which most of you probably do, you may want to grab the manual or go to Google or talk to a friend and get them to show you how to work it with complex numbers. So with that, I will tell you to make sure that you figure out when the final is. Make sure you come to the final. Good luck on studying for the final, reviewing for the final, and all of your finals. I'll see you at the final. Take care till then. Thank you for watching.